Hey everyone, this week we're going to be doing 10.2. There's a couple topics we're going to cover. The first one is we're going to learn about what's called a radian and switching from radians to degrees and vice versa. And then we're going to talk about all 6 trig ratios. So first off this week, we're going to talk about what a radian is. So a radian measure is something that we're going to be using for the rest of this unit a good bit. And typically it's something you guys have never heard of before. So in geometry, when we talk about angles, most angles that we talked about in degrees. So for example, if I draw an angle, I don't know, what does that look like? Maybe 25 degrees. But what we're going to talk about today is a different way to label this measure of an angle. So instead of using degrees, we're going to use a different unit called a radian. And so a radian is just another way to measure an angle. And so the definition of a radian is it's a unit of angle. So it's a way to describe how large an angle is, equal to an angle at the center of a circle whose arc is equal in length to the radius. So I'll go over that again real quick. So a radian measure is a unit of angle equal to the angle at the center of a circle whose arc is equal in length to the radius. So the reason why it's called a radian is, if you could guess, it has something to do with the radius of a circle. And so that's why we're talking about how to put angle measures on an XY axis, because we're going to be using that central angle in terms of coordinates. So if you look at this diagram, we have an angle here sketched in on the XY plane. I drew the whole circle in around it so that we understand that like how a circle works in terms of the radians thing. So this is just a general, they're saying that this is radius R. You can see here that from here to here, this coordinate has been labeled 1, 0. So actually this distance from here to here, the radius is equal to 1. It could be anything. I just picked 1 because it's the easiest. But yeah, this radius could be any measure. And so what this definition of radian is saying is this is some angle theta. And they're saying that the arc length between the angles, so this is the initial side of the angle, this is the terminal side, and they're saying we start here and go up. And so this length, this arc length that the angle subtends, so subtends is a fancy word for how wide an arc is. So the arc subtends from here to here, the initial side to the terminal side. And so the radius is directly proportional to this arc length. So R here is 1. And so instead of saying that this angle is like, I don't know, like 60 degrees or whatever, they're saying that it's a radian length of 1. So this would be, its radian measure would be 1. So this is an example of what a radian is. So instead of saying in here like, oh, this is like 60 degrees or something, they're saying, no, we're going to look at the outside and say how far does this arc go. So really what we're measuring is an arc length to say how wide is the angle. Well, this one would be an arc length of 1. 1 radian is how wide apart the angle pieces are. So all we're going to do is talk about this new way to measure an angle called a radian. So in class, like when we did all some of our trig stuff, we've talked about being in radians versus being in degree mode on your calculator. So like when we used our iPhone calculators, up top there was that button that said rad. Rad stood for radians. And so often we've needed to be in degrees. So now it's going to be the opposite. Now we're going to want to be in radians because radians are rad. That's always my joke in class. I always say put your calculator into radian mode because radians are rad, which they are. So I'm going to teach you guys is very often you've been given something in degrees and we want to know the radian measure or vice versa. Degrees is helpful because we can visualize that a little bit better. You guys have practiced a lot of degree measures in geometry. Like we know we can immediately visualize what 90 degrees looks like. But like, what is 90 degrees as a radian? Like it's some random number. So that's not something that we can easily visualize. So it's good to be able to convert between the two, so that way we can have something that you guys can visualize better and be like, oh, 2 radians is how many degrees? I don't know. We can convert it and see what the radian measure would be. All right, so the first direction is if you have something in degrees and want to change it to radians, there's a formula. So you're going to take your degree measure. So degree measure over 1, just because, we're going to have some fractions. Fraction and number is always over 1, times pi over 180. And that'll equal some radian value, radian measure. And then the other direction, if we have a radian, but I want to know what degrees it is, you take the radian value, and they're often fractions already. So I'm just going to write radian, like not over 1, because they're very often given to you as a fraction. Radian times 180 over pi. So they're kind of opposites because you're working backwards. And that'll equal the degree measure. So I'm going to do one of each down here with you guys, and then I want you to try the second one of each on your own. So the first one is 80 degrees. So if I know 80 degrees, what's the radian measure? I don't know. Let's take a look at our formula. So we're going to take degree over 1. So 80 over 1 times pi over 180 equals, well, hopefully you remember that to multiply fractions, you multiply across. So you multiply the top pieces together, you multiply the bottom pieces together. So 80 times pi. We're going to be working with pi a lot for the rest of the semester. And we're always going to leave it as pi. We never try to abbreviate pi at all. Pi is an infinitely large number. It's best to leave it itself. So 80 pi over 1 times 180 is just 180. Now, oftentimes when we're converting from radians to degrees or vice versa, you get a really big fraction right here. More often than not, it reduces down to something that's a little bit nicer. So the first thing that I notice is 80 pi divided by 180. The easiest thing you can do is just cross off the zeros. So divided by 10. So 80 divided by 10 is 8 pi. Pi, it stays there. 180 divided by 10 would be 18. And then what could we do? We could divide by 2 again. So 8 divided by 2 is 4 pi. 18 divided by 2 is 9. So 4 pi over 9 would be the most reduced that we can make it. Now, this is a perfectly acceptable answer. This just looks a little bit nicer, right? Like it's a nice fraction, 4/9, 4 pi over 9. So this is an example of taking degrees to radians. And then, how can you tell the difference between given a degree or a radian? Well, the first thing is radians usually have pi's involved. As you guys can see from the formula that, there's usually a pi somewhere. So the easiest way to tell that you're in radians is there's a pi, or if not, degrees always has a degree symbol. So if you've been told an angle measure and there's no degree symbol, that means it's a radian measure. And they're often usually labeled like the radian measure is blank or whatever. But yeah, degrees always has a little degree symbol. Radians usually have a pi, or they don't have a degree symbol. So anytime it doesn't have a degrees, then okay, you're in radians. So I'm gonna let you guys try negative 36 degrees on your own. But let's try 4 pi. So 4 pi is a radian measure. So if we want to go from radians to degrees, we're gonna use this formula. So we're gonna take the radian, 4 pi. I'm going to put this one over 1. It didn't come as a fraction, so I'm going to just put it over 1 for ease of multiplying fractions. 4 pi over 1 times 180 over pi. The beauty about going from radians to degrees is that the pi's always cancel out. You have a pi on top, you have a pi on the bottom, make them go away. And then you end up with 4 times 180. 4 times 180 is equal to 720 divided by 1. Obviously, that's just going to be 720. And we've changed it to degrees, so you need to put the little degree symbol. So this will be 720 degrees. All right, so pause here, try negative 36 degrees, change that to a radian measure, and then try 5 pi over 6, change that to a degree. All right, so hopefully you guys tried those. I'm going to put some lines so you guys know which problem goes with which. So let's try changing negative 36 degrees to a radian value. So you take your degree over 1, negative 36 over 1, times pi over 180. And then we just multiply across. Negative 36 times pi is negative 36 pi. 1 times 180 is 180. hopefully you guys can see that 36 and 180, you can divide those by something. My first thought was probably 9. So if you divide 36 and 180 by 9, you get nice whole numbers. But actually 180 is divisible by 36. So if you reduce the fraction, divide top and bottom by 36, you get negative 1 pi over 5. And again, you don't need the negative 1. I just wrote that to show you guys all my work, but it's really just negative pi over 5. Woo! So this, so just to visualize, 80 degrees, well, if you draw a little coordinate plane, 80 degrees is just below 90, right? So this L here would be 90 degrees. So 80 degrees is probably something like that. So if we start here, this would be 80 degrees. But also now we know that it's 4 pi over 9. Obviously 80 degrees is something that we can visualize better, but the length of this arc is 4 pi over 9, whatever units, centimeters, inches, feet, whatever it may be. If you took a piece of string and wrapped it around this arc and then measured that piece of string, if you pulled it flat, it would be 4 pi over 9 centimeters, whatever. You could actually find this decimal, right? And you could match it to the centimeters, inches, whatever you need. Same thing with negative 36 degrees. Negative 36, we start here and go down 36 degrees, sure, something like that. Negative 36 degrees. But again, that arc length is also negative pi over 5 length. So however long, however many inches, centimeters we're in. Separately, 4 pi, 720 degrees. Well, if you guys remember, once around a circle is 360 degrees. 360 plus 360 is 720. So actually this is one trip around a circle and then a second trip around a circle would be 720 degrees. 5 pi over 6. Let's try converting 5 pi over 6 to a degree. So you take your radian measure, 5 pi over 6 times 180 over pi. Well, pi and pi, those always cancel. 5 times 180 is 900 over 6. And then your last step, if you put in your calculator 900 divided by 6, you should get 150. Now don't forget to put the degree symbol, because now we're in degrees. 150 degrees. Hopefully we know that here's 90. To here would be 180. 150 is a little bit less than 180, so if you started here, it'd probably be something like right there. So this is 150 degrees, but that's also 5 pi over 6. So the length of this arc is 5 pi over 6, whatever unit. All right, so this is everything I've got for you guys in terms of radians. So radians versus degrees. What is a radian measure? So we're going to start using radians to talk about the length of angles, or the width of angles, how big they are. And we're going to practice them a bunch, and hopefully you guys will get the hang of what those look like. They come with practice. Yeah, so this is everything about angles in terms of degrees and radians. Also in this lesson, we're going to finish up talking about all trig ratios. So there's actually 6 trig ratios, and so in your lesson last week, we talked about the first 3. You guys know the first 3 really well, sine, cosine, and tangent. And we're going to talk about their buddies. First, though, we're going to practice some more, just some more practice with what some of these angles look like on coordinate planes. And so I'm going to call this point. And so this is similar kind of what you guys were doing last week. This is the coordinate, oh, they're going to seem kind of weird. This distance is going to, so your x distance is root 3 over 2, and your y distance is 1/2. So all 3 of these examples are in the first quadrant. So everything is positive. So your x distance down here, from here to here, is root 3 over 2. Your y distance from here to here is 1/2. How do we get this side? Well, use our handy dandy friend, the Pythagorean theorem. So I'm going to do that on a separate sheet. All right. So root 3 over 2 squared plus 1/2 squared equals c squared, our hypotenuse. Okay, well, root 3 times root 3 would give you 3 over 4 plus 1/2 times 1/2 is, so this one too, root 3 over 2 times root 3 over 2. Hopefully you guys remember from our radical section that a square root times a square root gives you this number underneath. 2 times 2 is 4. So it's 3 over 4 plus 1 over 4 equals c squared. 3/4 plus 1/4 is 4/4 equals c squared. Okay, 4/4 is, this reduces to 1. C squared. Square root of 1 is 1. So your hypotenuse length is 1. So this is 1. We're just going to talk about what angle that makes in here. Now, this is not something like, this is a very specific answer. These are 3 actually very special triangles that we're going to keep talking about. I just want to introduce them to you guys now. So if this is theta, this is your opposite side, this is your adjacent side, and this is the hypotenuse. And I'm going to help you guys find, we're going to find the sine angle for all these. So, so sine theta equals, sine is opposite over hypotenuse. So opposite side is 1/2 over hypotenuse would be 1. So it's 1/2 divided by 1, which is 1/2. I want to know what angle is in here. So if you guys think back to geometry, right triangle trig, how do we undo a sine? So how do we get rid of the sine? If I just want to know what the angle measure is, how do I get rid of the sine? Hopefully you guys remember that what you have to do on both sides is take the sine inverse. To get rid of a sine, you have to take the sine inverse of both sides. You can't divide by sine because sine's not a number, right? It's a function. So to undo sine, you do the opposite. So sine inverse and sine cancel each other out. So we get theta is the sine inverse of 0.5, which, let me see if my calculator is in degrees. All right, so to do sine inverse of 0.5 on my calculator, I have a sine inverse button. 0.5, 30. So this triangle is 30 degrees in this corner. So theta is 30 degrees. So this triangle is 30 degrees here. We're going to do this for the next 2. So this isn't something that I'm going to expect you guys to do. We're just going to practice these 3 specific triangles. So this is a 30-degree triangle. So specifically, an angle that starts from here and goes here. This is 30 degrees, and it has these special relations that the triangle has a length of 1/2 root 3 over 2, 1. This triangle is also a right triangle. I'm going to give this one the coordinate. Oh, my pen. Root 2 over 2. Comma root 2 over 2. So that means that the x length, or sorry, yeah, x distance and the y distance are the same. So this is root 2 over 2. This is root 2 over 2. And again, what's the hypotenuse? Well, if you do Pythagorean theorem real quick, I'll grab my separate sheet. So these are the 2 legs. So root 2 over 2 squared plus root 2 over 2 squared equals c squared. Again, this is root 2 over 2 times root 2 over 2. Root 2 over 2, sorry, root 2 times root 2 is 2. The square roots cancel out when you multiply them together. Over 2 times 2 is 4. And then obviously this is going to be the same thing. They're the same exact thing. So we've got 2/4 plus 2/4 equals c squared. 2/4 plus 2/4 is 4/4 equals c squared. That's really just 1. Square root, c equals 1. So once again, our hypotenuse here is 1. So hopefully you're picking up on the pattern that I'm picking special coordinates that give you hypotenuse lengths of 1. So that's why these ones are special, because the hypotenuse lengths here are 1. That's going to be important. And I want to know, okay, this one was a 30-degree angle that made this. I want to know what's another special angle here that made this hypotenuse of 1. Let's check it out. So again, I'm going to use sine. Doesn't matter which one, you could use any of 3 of the trig functions. Sine's just easiest because the hypotenuse is 1. So sine theta equals opposite, adjacent, hypotenuse. So sine is opposite over hypotenuse, so root 2 over 2 over 1, dividing by 1 doesn't do anything. So to find the angle, once again, we do sine inverse of both sides. These cancel, so theta is, if you go to your calculators, sine inverse of second square root 2 divided by 2. 45. All right, so this special angle is 45 degrees. And then I've got one more. So this coordinate point is 1/2 root 3 over 2. So if you notice, this one is very similar to this one, except something's different a little bit. The x and the y values are swapped. But actually, so this short leg is now here on the x-axis, and the long leg is here at the y distance. So really, it's just this triangle has been switched around a direction. All right, so now your x distance is 1/2, so from here to here is 1/2. Your y distance from here to here is root 3 over 2. And then, well, do we need to solve for the hypotenuse again? No, we already did it over here, right? Root 3 over 2 squared plus 1/2 squared equaled 1. So the hypotenuse is 1, because it's the same numbers. But again, does this angle and this angle match? Well, this one looks smaller than this one, right? This one's 30 degrees. This one is a little bit bigger than that one. This one's 45, so this one's got to be bigger than 45 degrees. So let's find out. So this is theta. Not sure what the degree measure is, but we can find it. Opposite, adjacent, hypotenuse. Again, I'm going to do sine just because, I don't know, it's easy. Sine theta is opposite over hypotenuse, so root 3 over 2 divided by 1, but the divided by 1 doesn't do anything. Solve for theta, sine inverse both sides. All right, so one more time, the sine inverse of square root 3 divided by 2. 60. So we get 60 degrees. Theta is 60 degrees. So these are 3 special coordinates that we're going to keep talking about through this trig unit. What makes them special is this. They all have a hypotenuse of 1. And obviously, these two are very closely related. It's just this one, like, they're just turned on their sides. So this one's just been moved around. This one is different. The middle one's different. It's a different type of triangle. These two are related. This one is the outlier. But all 3 of them are special. And I just wanted to show you guys using some math that we learned last week. So here's the coordinate. And so this is the x distance. This is the y distance. We use Pythagorean theorem to find the third side. So this is something that mostly we know how to do. I did solve for the angles this week, 30 degrees, 45 degrees, 60 degrees. I haven't had you guys solve for any angles yet, and continually we're not really solving for angles in this class as of yet. So if you're confused about the sine inverse to get theta by itself, that's okay. I'm just showing you guys what these special angle measures are. So today we've learned how to take degrees to radians. So that's why I found the angle measures, because we're going to take the angle measures and turn them into radian values. Woo. So if you're wondering, like, why the heck are we doing this sine inverse thing? Well, today in this lesson, I care about the degree value because I want to practice, our formulas, changing degrees to radians, and being able to visualize 30 degrees, 45 degrees, and 60 degrees as a radian value instead of degrees. All right, so just practice that. We actually just did this. So using the triangles from above, find sine of 30, 60, and 45. So sine of 30 degrees, sine theta is opposite over hypotenuse. So using our trig values, so we've actually done sine of all these. Sine of 30 degrees is opposite over hypotenuse. So it's 1/2 over 1, which is just 1/2, right? Sine of 60 degrees, that's this triangle, is opposite over hypotenuse. So it's root 3 over 2 over 1, which is just root 3 over 2. And then sine of 45 degrees, so this is this triangle, 45-degree triangle. So opposite over hypotenuse would be root 2 over 2 over 1, which is just root 2 over 2. I'm showing you guys the over 1 just to show you that it's still technically opposite over hypotenuse. Just the hypotenuse is 1, so dividing by 1 doesn't do anything to the math. Now, why don't you guys pause here for a second and try the cosine values of these buddies. So remember, cosine is adjacent over hypotenuse. So I've labeled all my triangles up here with their adjacent sides as well. So adjacent, 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 and the hypotenuse for all of them is 1. So it should be similar to your sine values. So try finding cosine of 30, 60, and 45. So pause here, try to find those 3 values. All right, so cosine of 30 degrees, here's our 30-degree angle one. Cosine is adjacent over hypotenuse. So this one is root 3 over 2 over 1, which is just root 3 over 2. Cosine of 60 degrees, so our 60-degree triangle is over here. So adjacent is 1/2 over hypotenuse, which is 1, so it's just 1/2. Cosine of 45 degrees. Adjacent, so here's our 45-degree triangle. Adjacent is root 2 over 2. And hypotenuse is 1. So root 2 over 2 over 1, which is just root 2 over 2. So hopefully here, after completing these trig functions, so sine and cosine of our special triangle friends, hopefully we see some patterns. So sine of 30 degrees and 60 degrees are opposite cosine of 30 and 60. And the reason why that's true is because, as you guys can see here in the triangle diagrams, they're just triangles that have been flipped. So this is the longer side on the x-axis, and this is the shorter side on the x-axis. So these triangles are related, but because their points are opposite, their sine and cosine values are opposite. So the 30-degree and the 60-degree angle are very closely related to each other. The 45 is not related to these two, but it also has a special property that we can see. The sine and the cosine value are what? They're the same. And the reason for that is because they have the same x and y distance. Woo. So hopefully you guys can see just from practicing this stuff that there is a reason why these 3 things are special. And so we're going to keep talking about these 3 triangles for a good while. I just wanted to show you guys why 30 degrees, 45 degrees, and 60 degrees is special. All right. So we're going to flip over to the back. I couldn't fit this part on the front. Like, I really wanted this part on the front with the rest of the stuff. So I'm going to be flipping back and forth a little bit. So the reason why it was important to talk about these, again, why I found the angles is so that we could convert these to radians, because we just learned how to convert to radians. So we can visualize 30, 45, and 60 degrees pretty easily, but I also want to make sure that we can visualize them, or start visualizing them, as a radian value. So 30 degrees as a radian, well, if you flip back over, how do you take a degree to a radian value? You take your degree times pi over 180. So 30 over 1 times pi over 180 is, well, you multiply across, 30 times pi is 30 pi. 1 times 180 is 180. The easiest thing to do is cancel out the zeros. So we get 3 pi over 18. Hopefully we can see that we can simplify this some more. Top and bottom, you can divide by 3. So 3 divided by 3 is 1 pi. 18 divided by 3 is 6. So 30 degrees is equal to pi over 6 length of arc. So if you look, if you flip back over, the arc length here, 30 degrees, is the same thing as pi over 6 in radians. So 30 degrees, pi over 6 are the same thing. Degrees, radians. All right, next up is 45. So 45 over 1 times pi over 180 equals 45 times pi is 45 pi over 180 times 1 is 180. Hopefully we can pick up on something that we can reduce by. So something that I see right away is we can divide both these things by 9. So 45 divided by 9, well, I typed in the wrong thing. 45 divided by 9 is 5. So we get 5 pi over 180 divided by 9, 20. Well, hopefully we can see that is this something that still can be reduced. Yeah, we can divide top and bottom by 5. So we get 1 pi over 4. So if you flip back over, 45 degrees, that's the same thing as pi over 4 radians. So 45 degrees or pi over 4 radian value. And the last one, 60 degrees. 60 over 1 times pi over 180. So we get 60 pi over 180. Zeros cancel out, so we get 6 pi over 18. Top and bottom, we can divide by 6. 6 divided by 6 is 1 pi. 18 divided by 6 is 3. So this one is pi over 3 radians. Woo! So if you come back over here, this arc, 60 degrees or pi over 3 radians. Woo! Alrighty. So that's everything that we're going to talk about with radians degrees today. And again, all this work that we're doing down here is not something that like I'm going to test you on. Like you don't need to memorize this stuff. This is not like your homework problems aren't going to be crazy like this. I'm showing you guys that there's some special relationships happening here. And now that we know how to do degrees and radians, we can talk about them. We know what 30, 45, and 60 degrees looks like. There's a special relationship because of their hypotenuse values of 1. And we can change those things to radian measures now. And hopefully we can practice starting to see 30 degrees as a pi over 6 value, 45 degrees as a pi over 4 value, 60 degrees as a pi over 3 value. And we're going to be talking about these more. So if you're confused about how I got some of this stuff, just ask me questions. This is not something that I'm going to quiz you on. This is just something that I'm laying a foundation for. All right. We are going to finish talking about our trig functions today as well. And I'm going to be drawing some diagrams. I drew them last week as well, but I'm going to get a little bit more specific. So our normal trig functions, we know sine, cosine, and tangent. Sine, so we abbreviate it sine theta. Remember, theta just represents any angle measure. Sine theta is equal to opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. And tangent is opposite over adjacent. And I'm going to start labeling these in terms of like the coordinate plane. So you guys practiced this a bunch last week, so I'm just going to make a triangle. Oh gosh, this didn't go well. Shocker. Here's the bottom of my triangle. Stop my triangle. And there we go. Look at that. Perfect right triangle. Nailed it. So we're labeling this. So you guys did some problems last week where this is some coordinate xy. So this means this is the x distance, this is the y distance, and then this is the hypotenuse. And we're going to call this r. And why am I calling it r? Because this probably isn't going to go well. If you draw a circle through that point, this is the center of the circle. So this diagonal distance that your triangle makes is actually the radius of that circle. So thinking back to geometry, a radius is the distance from the center to the edge of a circle. And so that's what this part of your triangle has become. It's actually the radius. So the hypotenuse value is the radius of this imaginary circle that's around all the way. So if you're wondering, like, why are we drawing angles on the xy axis? Because secretly they're circles, and we know the xy distance, so we know the xy legs, and now we're going to start talking about the diagonal piece, the hypotenuse, as a radius of a circle. And doing that actually makes it so you can do lots of cool math stuff. So we're going to talk about how our trig functions, so theta lives in here. So that means this is the opposite side, this is the adjacent side, and that's the hypotenuse. So we're going to label it in terms of x, y, and r. And so sine is opposite over hypotenuse. So sine is your y distance over your radius length. Cosine is the x length over the r length, because cosine is adjacent over hypotenuse. So it's your x distance over your radius length. And then tangent is opposite over adjacent, so that's your y length divided by your x length. All right, so we know these three. You guys practiced all this stuff a bunch last week. This week, I'm going to add in what's called the reciprocal trig functions, and they have special names. So you might have heard these in geometry, you might not. So each three of our trig functions has what's called its reciprocal. So hopefully you guys remember the word reciprocal from doing fraction work. So we say reciprocal a lot, like opposite reciprocal. I usually say like you flip it. So reciprocal trig functions literally just means when you flip it. So reciprocal, flip. Flipped trig functions. I'll say flipped. Reciprocal trig functions is the same thing as the flipped trig functions. And what I mean by that, like literally we're just going to take these and we're going to flip them. All right. But they do have special names. So sine's buddy is called cosecant. So cosecant, the abbreviation is CSC. So this stands for cosecant. So cosecant theta, so cosecant of an angle is like 1 divided by sine. So when you do 1 divided by sine, that flips it. So it makes the reciprocal. So it's 1 divided by sine theta, which really just means you're just flipping it. So that means cosecant is hypotenuse over opposite, which is r over y. So all you're doing when you're finding a cosecant value is you still just need these three things, but instead of doing opposite over hypotenuse, you flip it and you do hypotenuse over opposite. That would be cosecant. Next up is secant. Yes, we have cosecant and secant, and they are very similar words. Secant is cosine's buddy. Secant, you abbreviate it SEC. So secant is 1 over cosine. And so cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, which is r over x. So again, we're just flipping these fractions up here. We're just flipping them. And then lastly, tangent's buddy is cotangent. And cotangent is abbreviated COT, cotangent theta. So it's 1 over tangent. So that means we just take the tangent function and flip it. So instead of opposite over adjacent, it's adjacent over opposite. So instead of it being y over x, it's x over y. So you just flip them. So these are in order. So cosecant is sine's buddy. So I'm going to write that. Cosecant is sine's buddy. So cosecant is just your sine value flipped. Secant is cosine's buddy. And cotangent is tangent's buddy. Woo. You might have seen these in geometry. You might not have. Sometimes we teach these, sometimes we don't. Depends on the time. But this is something we learn in Algebra 2 for sure. So don't let this scare you. All it is it's just making fractions like you have been, except we're making a different kind of relationship. We're making the reciprocal relationship where we just flip everything. And so what this week's going to look like for your homework is a lot of questions like this. So your questions are going to look, so there's some radians to degrees questions, like the front half of the page or the front half of the notes. And then you're going to have a lot of questions like you did last week. But instead of just finding sine, cosine, and tangent values, you're finding all 6. So if you've been given one of them or a coordinate, find all 6 trig functions. So your homework's not going to look much different. Like you're going to sketch a picture. But then instead of just finding these 3 ratios, you're going to find all 6. Now that might seem like a lot of work, but remember, once you know sine, cosine, and tangent, for cosecant, secant, and cotangent, you literally just take those 3 fractions and flip them. So when you do sine, really you've done sine and cosecant. So if sine is like 5 over 7, then cosecant is 7 over 5. So let's try it. If sine theta equals 3 over 7 in quadrant 2, find the other 5 trig values. So for these questions, the first thing you need to do is draw a picture. All right, so we know that we have a triangle and it's in quadrant 2. So the first thing I'm going to do is draw a triangle in quadrant 2. Here's theta. And they're saying sine is 3 over 7. So I'm going to label opposite, adjacent, and hypotenuse. So sine is opposite over hypotenuse. So I know my opposite side is 3. My hypotenuse is 7. So that means I need to find the adjacent side. So that's where Pythagorean theorem comes in. 3 squared plus b squared equals 7 squared. So 9 plus b squared equals 49. So b squared equals 40. Last step, square root. So b equals, I'm just going to leave it root 40. Now, obviously when you solve, you're going to get some positive answer. So this length is root 40. But this is where we need to interpret, we're in the second quadrant, right? So the values here, this is the origin. Your x values here, are they positive or are they negative? If you have a point going this way, your x values are negative. So this coordinate point will be negative root 43. So, depending on which quadrant you're in, your picture, you will need to add negatives. So that's something that I think that you guys are probably struggling with the most. For example, if you're in quadrant 3, your x and y values would be negative. Quadrant 4, just your y values, because your negative y values live down here. Quadrant 1, everything's positive, because positive x's, positive y's. Something also to keep in mind, hypotenuse values are always positive, because when you solve for a hypotenuse, a squared plus b squared, when you square things, they always become positive. So your c value over here is always positive. Also, remember, we're measuring, so hopefully this helps. Remember that the hypotenuse value is your radius. Does it make sense to have a negative radius? Hopefully not. Like, can a radius go, like, in a negative direction? No, like, when you measure a radius, like, it's 9 centimeters or whatever. So that's why, in this case, our radius is 7 inches, 7 meters, whatever it is. So a radius measure is always positive, and and Pythagorean theorem confirms that because of the squareds. So if you're given a negative fraction, the negative always goes with either like wherever the legs of the triangle lie. So the legs are what can be negative, hypotenuse values are positive. But all right, so they gave us sine is 3/7. We know all three values now. So cosine is cosine is adjacent over hypotenuse. So cosine is going to be negative root 40 over 7. Tangent is opposite over adjacent. Opposite, adjacent. So it's 3 over negative root 40. Now here comes the new ones. So remember, CSC stands for cosecant. SEC stands for secant. COT stands for cotangent. Now, on your homework, they don't necessarily give them in order, so just keep that in mind. If you need your notes out, have your notes out. So cosecant, remember, cosecant is sine's buddy. So you're going to take your sine value, which is in the problem, and flip it. So cosecant, if sine was 3/7, then cosecant is 7/3. Secant is cosine's buddy. So if cosine was negative root 40 over 7, secant is 7 over negative root 40. And lastly, cotangent is tangent's buddy. So tangent was 3 over negative root 40. So cotangent is negative root 40 over 3. And that is it. So really what's happening this week is I'm having you guys practice more of these type of problems. Either you're given the coordinate or you're given the sine, cosine, tangent value, whatever it may be. And then you're going to sketch the diagram, fill in opposite, adjacent, hypotenuse. Make sure you use Pythagorean theorem to find any missing leg or hypotenuse. And then make your trig fractions. And all we're doing this week is adding in the reciprocal buddies. And all it takes is being able to fill in sine, cosine, tangent, and then flipping them. And make sure you're just associating the right ones together. So cosecant, sine, secant, cosine, cotangent, tangent. Obviously, I think cotangent and tangent go together well. My trick for secant and cosecant, my trick is no cocoa. So a lot of people tend to think that cosine and cosecant go together. No cocoa. Cosine goes with secant, sine goes with cosecant. I don't know if that helps. That's something that I've personally used for a long time to help me remember that. Hopefully it can help you guys. All right. So just to recap one more time, I taught you guys about what a radian measure is. So it's an arc length instead of measuring the degrees. You guys learned how to do degrees to radians, radians to degrees. We did some radians to degrees practice. And I helped you guys visualize, hopefully, what these angles and what the radian measures look like. We did some practice with some special triangles. So we practiced more of, using opposite, hypotenuse, adjacent to fill out sine, cosine values, and visualizing what 30 degrees, 45, and 60 degrees look like as radian values. So pi over 6, pi over 4, pi over 3. Radians to degrees, degrees to radians practice. And then I give you guys the last 3 trig functions. So hopefully you guys are starting to see that it's all kind of coming together. I got to teach you guys today that this hypotenuse value is a radius, so that's why it's always positive. Hopefully that helps you out in your diagram making. So your wall map questions are going to be degrees to radians, and then more practice like this. So that's what your quiz will look like too. So I'm going to post an answer key as soon as I make one. So hopefully Monday. I think my plan is to post answer keys on Mondays. If you guys have questions, please email me. Make sure you're actively just trying these problems. I know that there's a lot. Please email me with any questions. Remember that you can work together with people. You can Zoom together, whatever you need. So just let me know. Hope you guys are doing well. Have a good one.